Great, thank you. I'm going to give an overview of the work that has been performed by the PNNL modeling team, led by myself, with key team players, Jingyi and Xiangyu, both of them are here, and also Shai-Chi Tang joined the key team like about a month ago. And there's some other work ongoing work. We have been talking to several other colleagues, but I'm not going to talk in this overview. And of course, we are so grateful that we constantly received support from the broader Activate project team. So let's start with the outline of the talk and also related to the objectives of the project. As many of you have seen this schematic diagram from the proposal, that process modeling and other configurations of the models, including single column global models, they're of central importance in achieving some of the Activate objectives. So the work we have been doing were to try to first try to provide process insights and quantify the aerosol number, CCN, and cloud drop number relationship under different meteorological conditions with observational constraint from the Activate measurements. We use WRF weather research and forecasting, large AD simulation, configuration, and also cloud resolving modeling. And then the second objective is to evaluate and improve representation of aerosol cloud interactions in Earth system models. We have started developing a diagnostic package based on Activate measurement for regional and global model evaluation, and also started conduct single column E3SM simulation. Very soon we're going to perform global model simulations, but so it's great out here. I'm not going to talk about that today. So just give some example of those different model configuration. First, start with the WRF large AD simulation. We used this configuration to understand the aerosol meteorology cloud interactions in cold air outbreaks and also summer precipitating cumulus clouds. Its LES configuration is idealized configuration because we use the periodic boundary condition assumption. What that means is that when you start to simulate cloud, when you move out to the domain, it comes back again. So that's the big assumption, is that the cloud field you simulate, you assume in a large area is homogeneous. So we use a pretty large domain, 60 by 60 kilometers. We add two different resolution, 300 meter and 100 meter resolution horizontal. We initially use 300. We also compare to 100. It's almost no difference. But when we submit papers, reviewers always say that 300 meters is too coarse. But then we have to repeat some simulations with 100 is almost identical. Then vertical up to 7 kilometers, 152 layers. So we can compare to aircraft at different height. And for LES configuration, we use meteorological profiles, advective forcing, and surface fluxes. Those are all drivers of LES mostly from reanalysis, era 5. But we use Activate at the specific time of measurements to evaluate how well the model can start with the era 5, with the era 5 forcing, how to get the meteorology and boundary layer evolution and clouds compared to Activate. And aerosol number concentration, like example showing here, directly from measurements. And cloud drop number we get from measurements then to compare to model. And also other measurements. I will show example. So the science objective of our LES study is to, again, quantify. First study we published early this year to quantify sensitivity of cold air outbreak clouds and the marine boundary layer structures to the large-scale forcings we used. The second is also, we had the paper revised twice already, always complain about model resolution, to study the aerosol meteorology cloud interactions in cool air outbreak. And another ongoing study paper that's showing you has a poster near the door, study summer precipitating cases. So those are the example results we have shown included in the papers. For the interest of time, just give example here, like the time evolution of liquid water path. We compared to Aero 5 ghost retrievals. It turns out that LES shows the most agreement with ghost retrievals. We're confident that the LES capture the cloud evolution. And also the liquid water content profile, those black dots are from aircraft measurements, then the model simulation right in the middle. And we, of course, we can also characterize the variation and cloud drop number based on aerosol and based on the constant cloud drop number. So those are all compare pretty well with observations. So sorry. We also characterize the metric, the susceptibility also can compare to measurements. Then we have ongoing study on the summer precipitating cases. We have simulated 4 summer cases listed here, showing one example based on the June 2nd case. The top row shows the drop sound profiles. So the reason why we look at the individual drop sound is that initially the simulations shows subtle changes in the initial profile of forcing give you quite different clouds. We try to initiate those clouds based on the different sounding, try to do an ensemble LES simulation, try to capture the measured clouds. But still, there's some more challenges compared to the winter cold air outbreak stratocumulus cloud. Here are some same examples. As you see that the liquid water path comparison is not so well compared to GOES and other reanalysis. There's some, at some point, there's some agreement by the diurnal cycle, the evolution, not quite correct. We're still looking into whether that is due to forcing conditions or there is the intrinsic challenge, like the so strong spatial variability, like your one configuration of the model or a few just couldn't capture the time evolution of those clouds. Another configuration with a cloud resolving model is try to capture the mesoscale organization, like the examples showing here. The top row shows the larger domain of the WRF cloud resolving model of over 1,000 kilometers by 1,650 kilometers exactly. And then we have an embedded nested domain at the smaller but higher resolution. Outer domain 3 kilometers, inner domain is 1 kilometer. Both 3 kilometers and 1 kilometer, they can capture those cloud streets, the cloud structure rules, and also transition to cells. You can see that this kind of model configuration can compare very well with the satellite imagery. You can see those clear structures. So with this configuration, the science question we try to answer is that in a published paper, we try to answer what are the meteorological factors that determine the cold air outbreak, cloud morphology, and control the rural to cell transition. And Jingyi has a paper, poster. Also, she is preparing a paper and also has a poster here to describe the ongoing work regarding the role of cloud top entrainment and mixing on the cloud rules to cell transition. And also, we plan to study the role of aerosol as well. So those are the planned future work. And this just try to summarize the ongoing work with the cloud resolving model. For the interest of time, I'm not going to details about the work, but please stop by Jingyi's poster. And we particularly, in the effort, try to compare the cloud resolving model results with aircraft measurements in terms of the the mixing and entrainment. She wants input and discussion, especially from measurement folks. We invite contribution and welcome any kind of suggestions. And in an effort a step further from the LES and cloud resolving model, we try to evaluate climate model. The most fair comparison we will say is that since we're using the reanalysis forcing to drive our LES, and then the LES domain is about equivalent to the grid size of reanalysis, we would hope that those cloud fields are comparable between LES and cloud and reanalysis. It actually turns out that Arrow 5 on the left and the Mirror 2 in the middle and LES on the right, overall it captured pretty nicely that it captured the deepening of the boundary layer and the vertical extent of the clouds. But if you look at more carefully, those defined structures are quite different. Those are the key that the LES can capture, but the global models cannot. So in the next step, we're going to run the other global model. One of them is the DOE E3SM. We will also run CESM. So here, before that, we try to develop a diagnostic package, try to evaluate model that you just, like as Shubin said, that you cannot directly grab field measurements to evaluate global models. So we put them in the same context. We built a diagnostic package, try to do apples to apples comparison. So this package is developed by Shuai Qi, supported by different projects. So far, it covers measurements from 6 field campaigns. So we're going to activate, will contribute a lot over this region and contribute to this diagnostic package. Once we build this, we can use it to evaluate model simulated aerosol clouds and other properties. And so far, he has prepared activate Falcon measurements over in 2020, put all the measurements into this diagnostic package. So soon he will extend this to King Air, and then next step will be to design those global model simulations for the same time period, sample along the aircraft flight track to compare with observations. And one thing that I'm glad this morning heard that those measurements will be converted to the NetCDF format. So for this, it's for global model community, we mostly deal with NetCDF. It's easier to get into this package. And this is just an example comparing the observation in black and gray with E3SM version 2 results. They're not too bad. I mean, compare just pretty nice, actually. This, of course, the example here is nice. There are other examples will have larger biases. So before we run the global model, we try to run the E3SM model in a single column mode called SCM. This was proposed in the proposal that, especially for case studies, we use a single column model that specifically for the measurement domain and drive by same set of large scale forcing from reanalysis, so that they're comparable, including LES and measurements. So Shuai Qi just did one smoke test on the February 28th cold air outbreak case. It was successfully performed, but the results are not so great. But that's also a good case that will figure out why the model taking the same forcing cannot reproduce the nice deepening of the boundary layer and clouds that as we show in the LES and reanalysis. Just for the context to see that the reanalysis and LES showing the deepening of the cloud layers, but the model, global single column model, doesn't show that. So with that, just summary, we have some LES cases, cloud resolving modeling cases, and also the diagnostic package and some planned simulations that we're going to conduct that will be available for anyone in the project community or outside to collaborate to use, and or we can design, collaborate to design simulations for your own research interest. With that, happy to answer any question. I don't know if I went over time.
So I think in Yingyi's paper, the warp simulation, and you guys showed how nicely warp simulated the cloud structure, how well they compare Go16, liquid water path. But that simulation didn't use a two-moment macrophysics scheme, right?
You mean the cloud resolving model?
No, I'm talking about the warp simulation.
WRF, LES or cloud resolving?
The cloud resolving, yeah. I'm talking about Yingyi's paper that
Yeah.
you show a few hundreds kilometers of
Yeah,
clouds.
Do you mean the aerosols or?
Is there any aerosol, basically, what I wanted to ask?
Yeah, we did. Was prescribed with the constant, measured constant aerosol number concentration, cloud drop number concentration. Yeah, so that's a great question. So the reason why we didn't for cloud resolving scale at that big, for that big domain, we have to include a full chemistry package to simulate the evolution of aerosols. So that's the next step. It has to couple with a chemistry package.
Okay, thank you, Hailong.